it's a great honor for me to give one of these Abel lectures. Let me take the chance to say that I always consider it one of my luckiest events of my life that I meet and have a chance to learn from Lennart Carleson. Over the years, I learned a lot from Lennart, and not only mathematics, but the attitude toward choosing the right problem to work on, and a lot of other things in life. I especially appreciate that whenever I discuss mathematics with Lennart about my own problem, he gave me a critical, honest comment. I really appreciate that. Thank you very much. So today I want to talk about conformal invariants and differential equations. And so first, let me justify the title of my talk a little bit, because three speakers today have a title of conformal invariants, but probably we all meant a little bit different thing. So by conformal invariants in my talk, I really mean the following, that on a manifold, suppose I have a metric, a distance function, metric, I begin to change the metric conformally. That means that I only change the length of vectors, but preserving the angle between two vectors. So I call it a conformal change. And usually I denote this metric by G hat, which is a positive function rho times the original metric. So they change the length. And sometimes I denote this positive function rho by exponential 2w. And so my topic is geometric analysis. So I'm using the main purpose is to study quantity which are invariant under conformal change and geometric quantities. And the main method which will be used in this talk is PDE method. So this includes, for example, the sign of a curvature and the size of a curvature and the sign of the integral of some curvature. And later on, we will see that polynomial type curvature invariants. And so in this, what we call conformal geometry, we not only study these invariants, we also study operators, which are called conformal covariant operator, to study the invariant property of these conformal invariants. So I have organized my talk in three ways. In the first part, I will give a little bit review of a second-order partial differential equation to study these conformal invariants. And then I will discuss in the last 10 or 20 years the study of a fourth-order operator called Penney's operator, and the relation of Penney's operator that is associated curvature called Q curvature. And we will soon see that this PQ pair is to study Laplace operator and Gaussian curvature. And then I will mention some algebraic aspects of this pair, PQ, some structure theorem, and the relation of this operator which occur naturally in scattering theory, and to application to study some geometric quantity in conformal field theory like renormalized volume. And then the second part of talk, I want to mention that these Penney's operators are linear operators. But on the other hand, the Q curvature associated with it is naturally related to some quantity which can best study through some fully nonlinear elliptic PDE. So I will mention the connection of Q to this PDE. And the main purpose of to study this PDE is to study the eigenvalue of the Ricci curvature of manifolds. And the main tool to study this PDE is actually Gardin's inequality, and it's a part of the general study of a concept. The basic tool is Gardin's hyperbolic polynomials. And And finally, I like to mention in part 3 of the talk, I want to mention some more recent work of Paramount, and in which there is a new angle to study conformal invariance, and that's by fixing a probability measure and study the conformal invariance which is associated with this probability measure. And so I will mention the work in that aspect, in particular the Barker-Emery-Ricci tensor and the Paramount functional. So that would be the outline of my talk. So let me briefly review the classical subject, and that's on compact surface, and one study Gaussian curvature. And the main relation between topological analytic content is through this topological and analytic content is through this Gauss-Bonnet formula, which is this 2 pi Oded characteristic is equal to integration of Gaussian curvature, where this Oded characteristic is the Oded characteristic of the manifold is a 2 minus 2 genius. And then this Gauss classical theorem leads to uniformization theorem. We can use this formula to classify manifold and actually classify the manifold up to the diffeomorphism type. So and that is according to the sign of the integration of Gaussian curvature. For example, when a Gaussian curvature is positive, then it's a 2 minus 2 genus, so the genus has to be 0. So the Oded characteristic is equal to 2, and the manifold is homomorphic to the sphere. But actually, we know more. The manifold is actually diffeomorphic to sphere. And in this manifold, we can conformally change the metric to Gaussian curvature identically equal to 1. And we can similarly do the same by classify the manifold according to the Gaussian curvature equal to 0. In that case, we know it's the plane quotient a group. And when the Gaussian curvature is negative, we get a hyperbolic space quotient a group. And one of the ways to prove this uniformization theorem is through PDE and through the variational method to study PDE. So the PDE to study is the following second order, but nonlinear PDE. And that relates, so this is minus Laplace W plus the Gaussian curvature of the original G metric and equal to the Gaussian curvature of the conformal metric, and is E to W. So that means the uniformization theorem says that we can changing Gaussian curvature to a constant according to the sign of the integration. And usually we use variational approach to study this functional, and so we study this functional, which is the energy functional of this equation. And it turns out that this functional also have a geometrical meaning, and it's the Polyakov formula. And that means that this functional also is the quotient of the determinant of the Laplace operator and the difference of Laplace to Laplace of the conformal metric. And this determinant of Laplace is defined via this zeta function regularization process. And this is a classical work which was done in the 1970s to 1980s. And lots of people, let me mention Moser, and also Onofre Oban, and Oscar Philip Sarnak, and myself and Paul Young. So we studied this index theorem for Gaussian curvature, for prescribing this Gaussian curvature. And I cannot resist mentioning joint work with myself and Lennart Carleson on this subject. And so what we did is we proved that the Moser inequality is an inequality which says when the energy is finite on the sphere, the function is actually in Oded class, and this is exponential square class. And we proved that the extremum functional exists. Okay. And So I'm very proud of this work because this makes my Carleson number 1. So it's a joint work with Lennart. Okay. And now let me mention that the effort to extend this two-dimensional result. And one of the efforts to study this functional is to study, instead of studying this Gaussian curvature, there is to study this Hoover-Einstein functional. Okay. And so this is the functional. Given a metric, we now study integration of this scalar curvature of the metric. And it is natural to study this functional for a couple reasons. First is that the critical point of this functional is known to be Einstein metric. So these are metric, which is the Ricci curvature is proportional to the metric. So this Einstein metric is supposed to be a model case of manifolds. And one also knows that modular finite dimensional subspace, all the critical points are saddle points for this functional. So that leads to the following way to study this critical point of saddle point. And this is a classical approach. And that is, we begin to fix a metric and study the change in the conformal direction of the metric and of this Hoover Einstein function on this conformal metric. We take inf. And we hope the inf is achieved by a metric, which is constant scalar curvature, and then we vary in the direction perpendicular to the inf direction. So we have this sup-inf approach and obtain a saddle point. And this program was finished in the 1980s by Obang and Chang and Schrödinger. And so it turns out that in each conformal class, there is a metric which attains a constant scalar curvature. And so let me recall that in this approach, a way to compare to this Gaussian curvature equation, one has a second order operator to study Gaussian curvature, and that's called conformal Laplace. So it's this Laplace operator plus the scalar curvature. And it's using this conformal Laplace operator, and instead of writing this conformal change into exponential 2w, and the traditional notation is write it as a function, positive function u, 4 to the over n minus 2 power. And if we write this conformal factor in this way, then this function on this conformal metric functional is just the inner product of u with LGU. And the Euler equation is the equation study of LGU equal to a constant. That constant means that's the scalar curvature of the conformal metric is a constant to this power u to the n plus 2 over n minus 2. And let me mention for later purpose, it turns out that this index n plus 2 over n minus 2 is a critical index in the sense that to study the minimum achieved, it happened to be the Sobolev embedding of this W12 into this LP space is critical when P is equal to this n plus 2 over n minus 2 plus 1. So from PDE point of view, this equation is difficult to solve because the Sobolev embedding happened to be not compact at this critical index. But from geometric point of view, it's the reason that why this happened is because on sphere, we know the diffeomorphism group is non-compact. The group of diffeomorphism is non-compact. So that leads to diffeomorphism class of metric, which is blow up at certain points, which is a blow up sequence. So to solve the Yamabe problem in Rick Shen's approach, he actually has to encode the global quantity of positive mass to prove the solution exists. But in this talk, let me mention another angle to study this, substitute to study this Hilbert-Einstein functional. And for this, we begin to search other operator which also has these conformal covariant properties. For example, we have already mentioned second-order operators, Laplace operator and conformal Laplace operator. And it turns out that there are many other such operators, and I want to talk mainly today. In 1983, there's an operator studied by Pennitz. Okay. And Pennitz operator is just a fourth-order differential operator. The leading order term is bi-Laplace operator. But then there is the second-order, lower-order term, and that's divergence, and then with coefficient, which consists of the scalar curvature and recede of the metric, and then differential. So this is a second-order term. So on flat domain, this Pennitz operator is just bi-Laplace operator. And when the manifold, underlying manifold, is one of the model case, the Einstein manifold, then this operator is just Laplace composite with conformal Laplace. And so the proposal now is that this Pennitz operator has lots of good conformal invariant properties. And when acting on four manifold, under conformal change, the operator is just exponential 4W of the operator on the background metric. So it just pull out the conformal factor. And also, it prescribes a curvature. So it's like Laplace operator on 2 dimensions prescribe Gaussian curvature. On four manifold, this operator prescribes a Q curvature. And that Q curvature is a quadratic expression of curvature, curvature square minus 3 times Ricci square. But there is also a fourth order term, which is Laplace of the scalar curvature. And so it prescribed the Gaussian, the Q curvature this way. And this Q curvature turns out also to be part of the Gauss-Bonnet formula. So if one look at this 4-dimensional Gauss-Bonnet formula, it has 2 terms. And one is this Q curvature on manifold without boundary. One is this Q curvature. And the other is this Weyl curvature square. Okay. So Weyl curvature is a term which measures how flat is the manifold. So when the manifold is locally the same up to conformal change of metric, like the Euclidean metric, then the Weyl vanishes. And in particular, this Weyl curvature is a pointwise invariant term in the sense if one change the conformal metric, then it just pull out the conformal factor. So in particular, on four manifold, we have a pointwise equality that the Weyl square d volume is the same as the Weyl square of the conformal metric. So that means that in this Gauss-Bonnet formula, on the left-hand side, we have a topological quantity. On the right-hand side, we have 2 terms. One is a pointwise invariant term under conformal change of metric. So that means that this integration of Q, this integral, is a conformal invariant quantity. So that means it's invariant under conformal metric. So given what we know about uniformization theorem, now one is curious to see that, does that mean that we can deform metric in a conformal class to Q curvature equal to constant? And so let's look at the PDE problem. So instead of a second order, we now have a fourth order PDE, and we want to study this prescribing Q curvature equation under conformal change. So we want to see that can we solve this equation given G and such that this QGW, say for example, equal to constant. So and to do this problem, it is natural first to see when is this operator P invertible, or when it is a positive operator. And given this formula of this operator, this Q curvature, this P operator, and since its coefficient involving information of the curvature 3C and the scalar curvature, so it's natural to impose pointwise condition on the manifold curvature condition so that it is positive. But on the other hand, given that this is an invariant operator, conformal invariant operator, the more natural condition to impose for the operator to be positive should be an invariant quantity, conformal invariant quantity. And it turns out it is indeed so, at least in the class when the scalar curvature of the manifold is already positive. So when the first eigenvalue of this second order conformal Laplace operator is positive, that happens, for example, when the manifold has scalar curvature is positive. It turns out this conformal invariant quantity, this integration Q positive, already imply this operator is a positive operator. And so once it's positive, we can manage to solve this equation. And actually, in this case, once it's positive, we know that this quantity has a natural bound, and that bound is A pi squared. And from there, we can use a higher dimensional analog of Moser's embedding theorem, Sobolev embedding theorem, to solve the equation. And we solve it to be a constant. And so formally, the program is the same as a two-dimensional thing, except now we impose the condition, not only this Yamabe constant is positive, Yamabe constant is positive, is the same as the first eigenvalue of the conformal is positive, and Yamabe constant is defined to be inf of this integration of the scalar curvature with volume fixed for metric in the same conformal class. And this constant has the same sign as the first eigenvalue of the Laplace operator. So with these two quantities, we can control the positivity and solve the equation. And I will not say how to prove this, but on the other hand, the reason why now there are many different ways of seeing it, but the existence part of the result actually, again, depends on the fact, analytic fact. It turns out that this equation, if one begins to study this log determinant of this conformal Laplace operator, for an operator like conformal Laplace operator, then Q curvature or this Penny's operator is one of the key terms, major term in the expression of the functional. So to study the positivity of this operator amount to study extremal metric of this log determinant function. And this is an early work of Bronson and Osted. And instead of talking about the proof, let me mention some geometric content of this Q curvature, why it is interesting to study Q curvature positive, or what's the geometric significance of this operator. So here are some geometric aspects. So first, let me mention this Convulsion Hoover inequality on compact surface. There's this classical work which says that on a surface which is not compact but which is complete, and suppose we know its Gaussian curvature is already integrable, that means absolute value is integrable, then this manifold is already compactified. Okay? So this manifold is up to finite number of points, a compact manifold. And not only so, we also know the Oded number of this manifold is integration of k and plus the number, some arrow turn, and that arrow turn corresponds to this isoperimetric constant of this compactification of n at the end points of Q. So there is this geometric picture to compactify the manifold with finite number of ends. And we know the behavior at the ends if the Gaussian curvature is in L1. I will not go into detail, but it turns out this result can be generalized to 4 dimensions. Suppose we restrict to a special case of 4 manifold, and that special case is the case when the manifold is locally conformally flat. That means the manifold has Weyl tensor equal to 0 and has positive curvature. And if we impose the condition, the scalar curvature is positive, the Q curvature is in L1, again, we can compactify the manifold. So this Q curvature actually controls the behavior of the manifold at the end points too under this compactification. And I'd like to mention some other aspects of this Q curvature, but let me first mention some recent work of in this field. Okay. And I have already mentioned Pani's operator. Turns out this is a 4th order operator, but this type of operator is a special example of a large class of operator, and in particular in manifold of even dimension, there is operator called GJMS operator, which is of order 2k and which has conformal covariant property. When 2k equal to n, it prescribes a curvature Q, which is Q curvature, which is part of the Gauss-Bonnet integral. And the fact that this Q is part of the Gauss-Bonnet integral was pointed out by Bronson, and now this Q curvature sometimes is called Bronson's Q curvature. And then there is some work of Gran and Zolsky, and also followed by some other work of Pfefferman, Gran, and also Pfefferman, Hirachi. And what they did is they begin to relate this existence of this QPQ pair to a scattering series of conformally compact Einstein manifold. So I'd like to mention a little bit of what is conformally compact Einstein manifold. So this is a class of manifold which is a manifold, n-dimensional manifold with boundary. Okay. And there is this distance function which measures the distance of the manifold to the interior. So this is the distance function, R. R is positive on the interior and equal to 0 on the boundary, and then degenerate on the boundary. And we say it is compact, conformally compact. That means up to conformal metric compact means that there exists a distance function R such that R squared G plus is compact. So the manifold itself may not be compact, but up multiplying by the distance function, it is compact. And we say it's conformally compact Einstein if we actually, up to this compactification, we also know that the metric is something like Poincare metric. Its Ricci is a constant, actually a negative constant, a Poincare metric. So the model example is the example of a sphere with hyperbolic ball. So we have this sphere, Poincare metric, and with hyperbolic ball and sphere as its boundary. And if we rewrite the standard hyperbolic distance, write this distance function as 1 minus absolute value y over 1 plus y, then we rewrite the metric G plus into this way. So in this case, one can easily see that R squared times this G plus is a compact manifold. Now it's a distance function plus this 1 minus R squared. So it becomes the usual Poincare metric. So in the early work of Pfefferman and Gran, in order to systematically study conformal invariants, they have construct a metric called ambient metric. And one of the process in the construction of the ambient metric is to show that given a manifold Mn in a small neighborhood of the manifold, you can always construct such Poincare metric, and which is a conformal compact. So this is our model case. And suppose we have such a manifold. So that means suppose we have, in this case, for example, a sphere and with interior the Poincare ball. So in this case, we can study, in this case, there's a result, classical result of Mazzero and Melrose, which says that there is only finite many point spectrum in this setting. And otherwise, we have continuous spectrum. So if S is a number which is not outside this finite number of points, finite many exceptional points, then if it's this, then we can begin to look at this differential equation, solve the equation of Laplace G plus minus this S n minus S. We solve the second order differential equation. And now, using the usual trick of this ODE, we know that this equation, U, suppose we write, given a boundary function f on the manifold, we begin to try to solve the second order ODE. Then we can write this equation into two parts. One is asymptotically like the distance to the n minus s power. The other is the distance to the s power. So we rewrite the solution of this equation into f, a function f, which times r distance r to the n minus s power and g plus r to the s power. So the scattering metric is a way to look at the behavior of g under f when f restrict to the manifold is equal to f, little f. So given a little f, we write down the solution, we get a capital F, and then we get a capital G. We restrict G to the M, and we have this scattering matrix. Okay? So this is a scattering matrix. And so what the scattering matrix did is the scattering matrix behaved like the map, which is mapping Dirichlet data to Neumann data. So one should think about this F as Dirichlet data and this G as the Neumann data. Okay? So map F to G. And Graham and Zolsky pointed out the following fact. That is, this Penny's operator is the behavior of the residue of the scattering matrix at the poles, and the poles is n over 2 plus k. And this 2k should be less than or equal to n when n is even. So in particular, at 2k not equal to n, this metric at the point 1 is called the Q metric. One can write it down, it exists. And when n 2k equal to n, we actually have a pole, actually a single pole at this scattering metric. So we need to consider this scattering metric Sn at 1, and that's this Q metric. So this Q metric is related to this scattering metric this way. And with this understanding, look at the inside region of the hyperbolic ball when r is bigger than epsilon. And then this is a finite region, volume finite. We can expand it in terms of epsilon. And then, depending on the boundary is even or odd, this expansion has terms which is either constant term or the log 1 over epsilon term. So we begin to expand the volume term in terms of this epsilon. And it turns out that this term, this conformal invariant term, this constant term V here is called renormalized volume when the boundary is odd. And when n is even, it's also this constant term. And so the consequence is when n is odd, this volume is a conformally invariant term, independent of the choice of the conformal metric. And when n is even, L is independent term. And so the result I want to briefly mention is the other geometric content of this Q curvature is, at least when n is even, it is this conformal invariant term in this asymptotic expansion. And this is this kind of term is studied in mathematical physics in conformal field theory. And it turns out that not only so, when n is even, when n is odd, one can also relate this renormalized volume to a term which I call sigma 2. And in 4 dimensions, this is related to the Q curvature. And this result in four manifold, now we have a 3-dimensional manifold, and this renormalized volume, depending on the specific extension inside, is related by this Gauss-Bonnet formula, and is related to the Q term. And the result was proved for 4 dimensions by Mike Anderson, and later on generalized for all even dimensions through the understanding of the Q curvature. And I like also to mention a recent work of Elizakis, which says that it turns out this Q curvature has a structure. Okay? And that structure says that this every Q curvature, which is integration of Q, is invariant, and it's the highest order conformal invariant, is either Pfäffing or pointwise invariant or divergence term. And so this says that we know all the invariant terms through the study of a Pfäffing integral. Now let me begin to talk about relation of this Q curvature to some other elliptic equation, and in particular to a second-order full-linear equation. And the relation is because if we begin to look at the connection is here, we look at the full Riemannian tensor, and that has 2 parts. One is the Weyl part, and the other turns out to be the Ricci curvature term, and that's called Weyl-Shelton tensor. And this is a combination. The Shelton tensor is a combination of Ricci minus a fixed multiple of the scalar curvature. So this is a decomposition of the full curvature tensor into 2 parts. And as we have mentioned before, this Weyl curvature is a pointwise conformal invariant. So if we are going to study conformal invariant, all the information under conformal change of metric is contained in the study of the Shelton tensor. So here is the expression of, we write the Shelton tensor in terms of the background metric. And the leading order term turns out to be hashing of W. So it's Wij, partial derivative. And then there is a first order term, quadratic term, like Wi, Wj, and then some of the gradient W term. So it's the leading order term is hashing term, and then this plus some lower order perturbation, which is the first derivative term. And to understand this Shelton tensor, we begin to look at the metric, n by n metric, and study its eigenvalue. And to do so, we usually study the symmetric function of the eigenfunction, eigenvalues of A. So the first symmetric function means, so this is the symmetric function, which is a special case of Gardner's hyperbolic polynomial. So we begin to study the sum of the eigenvalue, so this summation lambda I. And in this geometric setting, we begin to take trace of this Shelton tensor, so it's a multiple of the scalar curvature. To study the sigma 1, the trace of this Shelton tensor, amount to study the scalar curvature. And to study this second symmetric function, that means we begin to study sum of lambda I, lambda j, the product of eigenvalues. And in this case, it's a combination of the trace square minus the norm of A squared. This is the Hilbert-Schmidt norm. So it's, again, a quadratic expression of the scalar curvature and the Ricci square. So it's a polynomial term in terms of the curvature. And sigma n is just the determinant of the Shelton tensor. And so to study this determinant of the Shelton tensor, it amounts to study this Monge-Ampere equation. And so suppose instead of study this Hessian term plus a lower order perturbation term, let's just to study the Hessian term. And so this is to study the symmetric function of the Hessian Uij equal to f. And suppose we constrain to the class f is positive, and then we study this Dirichlet problem for U of compact support in a domain in Rn. And this is done classical work by Caffarelli, Nirenberg's book, and the regularity of such four-lane and linear differential equation is also studied by Krylov, Evans. So they have this result C11 into C2 alpha, the result in this positive cone class. And there is also work of Caffarelli, Pogorelov, Chang, and Yao. And also, all of them use the fundamental tool of Gardner. And I want to mention that compare this differential equation on plane and the differential equation we are interested to study on manifold, and there is similarity and there is also differences. So if we look at the Hessian equation on the plane, and suppose we just look at sigma 2 function, it turns out it's just Laplace square minus Hessian square. So in a special case of 4 dimension, k equal to 2. And suppose we study this Shelton tensor and the conformal change, and then we still have the background metric and plus the leading order term, which is the same as the Hessian because it's contribution from the Hessian of W. But then there is this mixed term, which is second order times the first order square term, appear to be a little bit lower order. Okay, so, and then plus some further lower order term. And it turns out that one can, of course, apply the general technique of studying this Monge-Ampere type equation to study this equation on manifold. But on the other hand, the difference is that there is contribution from the lower order term. And for example, for this first equation plane on plane domain, it turns out that it is very difficult, and one is actually unknown, even for Dirichlet boundary value problem on plane domain, if there is C1 estimate. If C1 estimate implies C2 estimate. But on the manifold, because of the contribution of the lower order term, if we impose a sign on the lower order term, for example, we assume the scalar curvature of the conformal metric is positive, that impose a sign of this Laplace W positive, then we begin, we have the technique to push the C1 estimate to C2 estimate. Okay. And so the lower order term is helping us to gain this bootstrapping process. And on the other hand, for geometric equations, we also have additional difficulty, and the difficulty comes from C0 estimate. And C0 estimate is like the conformal Laplace equation. We are in a critical case where we have this diffeomorphism group acting on the solutions. So for example, on 4 manifold on sphere, we know we do not anticipate C0 solution of the equation. So there's this blow-up phenomena we have to get rid of. We have to say sphere is the only exceptional case, and except for that, we do have C0 estimate of equation of this type. And now let me say that why are we interested to study such symmetric function? And the geometric content of that is, it happened to be, this is through many a consequence of Godin's inequality, that this symmetric function of this Shelton tensor carry geometric information. So for example, when n equal to 3, and if the scalar curvature is positive, and if the second symmetric function is positive, then the full sectional curvature is positive. And for n equal to 4, the second symmetric function is positive, then Ricci metric is positive. So this sign of this curvature tell you the Ricci curvature in this case is a 4x4 matrix, so it has 4 eigenvalues. But these two sign of these two geometric quantity already impose a sign on this 4 eigenvalue, all positive. And why are we interested to study Ricci positive metric? Because again, it carries a lot of geometric information. For example, in that case, we know the fundamental group of the manifold is compact. So we are interested to study, to have such quantity. And so again, constraint to the case for a 4 manifold and second symmetric function, we are interested to study the second symmetric function. And on the other hand, we also know that we have tools to study the Q curvature. And it turns out that this expression of the Q curvature differs from the sigma 2 only by this term, which is the Laplace of the scalar curvature. So in particular, on manifold without boundary, the integration of Q is of integration of sigma 2. The integration of this Laplace term equal to 0. And actually, originally in the Gauss-Bonnet formula, one did not see this Laplace R term in the formula of Gauss-Bonnet. So the offshot of that is, again, we can write this Gauss-Bonnet formula and in terms of sigma 2 and the Weyl square, and we now have this integration of sigma 2 is a conformal invariant quantity. So that allows us to use our knowledge about Q curvature and through the relation to Penny's operator to study this Fourier linear equation that is a symmetric function, second symmetric function. So there is one of the result, early result is indeed, again, we have these two numbers, each is a conformal invariant quantity, the Yamabe number and integration sigma 2. Once it's positive, in the same conformal class, you can solve the equation so that this, in this conformal class, the sigma 2 of the conformal metric is now constant, positive constant. So in particular, you get Ricci positive metric under these two geometric, these conformal invariant condition 1 and 2. The fundamental group is now finite. And our original proof of this result uses a heavy-laden machine of this Penny's operator, but later on they simplified proof by Gursky and Diakovsky and using other results in the linear PDE. And so we do know that we can solve this using under these two invariants, under these two constant, conformal invariant constant, we know the fundamental group of the manifold is finite. And our next goal is trying, given what we know about the role of Gaussian curvature play in compact surface, we're now trying to see that does these two conditions allow us to classify four manifolds satisfy these two invariants. So, and for this, let's first, there is this well-known result. We know that the classification up to homomorphism is already done. And that is by work of Donaldson and Friedman. We already know the list of all possible homomorphic class of simply connected four manifolds, which has scalar curvature positive and integration sigma 2 positive. And we know what they are. They are basically four sphere and connection of S2 cross S2, two sphere cross two sphere, and connection of copies of complex projective space CP2 and oriented conjugate, complex conjugate of this space, CP2 space. So we know that. And now we try to see that is this result up to diffeomorphism true. And in this case, we only have very partial progress. And let me report a little bit of progress in this direction. So, it turns out that when the manifold is very close to the fourth sphere, S4, say S4 is a standard model for standard fourth sphere, we know that it turns out that we have this result which says, indeed, in this case, we look at these two quantities. They add up to be either characteristic class. But suppose one portion is greater than the other portion. In particular, when it is positive, integration sigma 2 is positive, then we know the manifold is already diffeomorphic to the fourth sphere. And this is done through this is L2 version of some early work of Marjoram, which says that instead of integration of this quantity, suppose we are pointwise inequality, then it is true. And so this is an L2 version of that, a diffeomorphic theorem. And not only so, but we also know this result turns out to be sharp, in the sense that once we reach this is equal to 1/4 via square, then turns out there are two possibilities. One is when it's equal to this, equality holds, then either both vanishes, via vanishes, and integration sigma 2 vanishes. In that case, we know the manifold is already conformally equivalent to S3 cross S1, the standard 3-sphere cross S1. And when it's equal to 1/4, the equality holds, but both terms are not vanishing, we know it's CP2. It's diffeomorphic to CP2. And this is again through the work of PDE. Use solving the PDE and look at what happened on the degenerate cases. And in particular, the second part of this result, why can we classify the result when this integration sigma 2 equal to via squared? And that's in that case, we already know that when a manifold is greater than, then it's diffeomorphic to fourth sphere. So it's equal, that means that this metric is already a critical metric of the via square. So in that class, you already reach the minimum. If it's greater, it's fourth sphere. So if it's not fourth sphere, it got to be the minimum of the via square. So in particular, that means that we have an additional equation to play with, and that's the equation of the critical, satisfied by the critical metric of this functional. And that equation is called Bach-Flat equation. And in that case, we look at the critical metric of this, and that's involving second derivative of the Weyl tensor and plus the lower order term. And the critical metric satisfies a condition called Bach flat. Yes. So Bach flat. And using that equation, we can study the equality case. And so that leads us to think that in general, we do not exactly know how to continue this program. We have a guess. We know the next thing, if we consider the ratio of this quantity to the Weyl square, the next ratio should be, if we can guess, it should be 1/6, and that should be S2 plus S2. But we have difficulty pushing our analytic technique to prove that. But on the other hand, we do know that if we confine ourselves to Bach flat metric, critical metric, we have the following result, and that's the finiteness result. And that says that indeed, in this class, if we add a condition, it's Bach flat, and then with this sigma 2 positive, strictly positive, and we add the condition that the size of this sigma 2 is comparable to Weyl, so that means we assume this Weyl square is already bounded by some constant in a finite topology situation, then we have finite many diffeomorphism type. So we reach the situation, at least in this very special subclass of metric, we have this finiteness theorem. But I know how much time do I have? Already?
Well,
a
few minutes.
2 minutes? I see, I'm sorry. So, instead of talking about the proof, let me now say a little bit about the Perelman's work. Okay. And so we have studied this Hoover-Einstein functional and talk about its critical point. And in the work of Perelman in 2002, instead of looking at this Hoover-Einstein functional, he began to take another point of view, and that is given a manifold and metric, fix a probability measure, and look at the density function e to the minus f associated with the measure, and look at the functional instead of the scalar curvature, and you look at the functional plus Laplace f. And with respect to this functional, it turns out the operator he's studying is the limiting case as n tends to infinity of the conformal Laplace operator. But this operator LG infinity does not have conformal covariant property, but it occurs naturally in Perelman's functional. I'm running out of time. The motivation of Perelman's study is, of course, led by the work of the gradient flow of Hamilton's Ricci curvature is the gradient flow of this Perelman's function. And so in that regard, let me mention that in this case, with respect to a measure, the natural Ricci curvature is the Barker-Emery Ricci curvature. It's Ricci curvature plus a hashing metric. And the scalar curvature now is not a trace of this, but scalar curvature plus 2 Laplace f minus gradient f squared. And that's because for geometric consideration, we need such a variation to have this Yankee identity. So the point I want to make now is, what's the advantage of Perelman's functional versus the classical result? And it turns out that for one thing, there are certain advantages. For one thing, it turns out that adding this fixing a measure to study in some conformal class, if R and G equal to constant, the variational problem becomes a subcritical problem. So that's one advantage. And the other advantage, I will not have time to elaborate, is that it turns out that fixing a measure, a probability measure, one can create a lot of of pointwise conformal invariant. So that means if we're changing e to the f dvg to e to the 2 f hat dvg, this quantity is invariant. So in full manifold, it used to be the only pointwise invariant quantity we know is y squared. But in this way, we create a lot of pointwise conformal invariant. And there is advantage for this pointwise invariant, but one also wonders what's the fixing a measure. One can begin to study this variational problem, and it's a subcritical problem. But the equation one solves is not precisely scalar curvature equal to constant, for example, but scalar curvature plus the information about the density function equal to constant. Suppose we want to eliminate this constant, then we need to vary over all measures. So given this functional, we begin to vary the measure. It turns out the inf of that is the Yamabe function. And the only one remark I want to make is, at this moment we wonder that the difficulty of studying all problems of this type is the diffeomorphism group is too big. But for fixing measure, we can always solve the problem. And does that mean we should fixing a measure and vary the measure instead? And it turns out that the difficulty is the same. That is, it turns out changing inf of the measure is the same as changing the diffeomorphism. So for all functional of this type, if we fix the measure and we're changing the metric G in a diffeomorphism class, it's the same as fixing a measure, fixing a metric G, and changing metric inf of all G. It turns out to be equivalent problem, and this is a consequence of another result of Moser, which says that two measures of the same mass is always related by diffeomorphism. And I think the relation of Karaman's functional to this subject is still being explored. And in particular, there are lots of people working on different aspects of this field. Thank you very much.